So I think what we're talking about today is kind of neat because you can actually get answers without doing the reaction. What I mean is, let's say you have some reactants. This is where you're starting out. And whatever the reactions, you want to start there. And then you have products. So the reaction could be whatever you want. I mean, it could be synthesizing this really funky compound that's going to help reduce blood pressure or something, right? It really doesn't matter. The point is you start out with reactants, you end up with products. Well, in theory, you can do all these other little steps first. Maybe convert it to these products first, and then go over to here, then go over here. But as long as you end up, start and stop where you want, it's legit. You can do all these predictions. You can predict how much heat it's going to take, and there's a number of other things. We're just really concerned about heat today. But all that matters is where you start and where you stop. So, and it's all theory. So you could do all, this could all be imaginary. All these little steps. You don't even have to do them. And then you can predict what the heat's going to be without even doing the reaction. So it's very useful, especially in industry and research. So, for example, call this step 1, call this step 2. And so here's 2 reactions. I could add a delta H1 for each of these reactions. Maybe easy reactions to do in lab, but we're just going to add up these 2 steps. And you can see like this oxygen completely cancels with one of those, so left with one of them. Both of those CO2s end up canceling out. So overall, you just get 2 carbon solids, and an oxygen gas gives 2 carbon monoxide gases, right? So the overall delta H is just going to be delta H1 plus, oh, that should be a 2 down there, delta H2. Let's add up the enthalpies for the steps. So without even doing the reaction, we can make some predictions. So now the problem I see, though, is we have 3 ways now to get the enthalpy for a thermochemical equation. Now, see if Audrey remembers this. Audrey, a thermochemical equation has what 2 things? What makes up a thermochemical equation? You had a what and a what? A chemical reaction, and that chemical reaction has a what, Stephen? Has a delta H. So it's just fancy terminology, right? That it's a chemical equation with an enthalpy is a thermochemical equation. So what we're talking about is 3 ways to get this enthalpy that's in a thermochemical equation. 3 ways. So here's our quiz. We just did this, right? Divide the kilojoules by the number of moles. And then the second way, we're going to use Hess's law. So that's way number 1. And what is Hess's law? It's just what I talked about, how it can all be imaginary. We're going to be given a couple reactions. This is how Hess's law always works. They're going to give us a bunch of reactions, a bunch of thermochemical equations, a reaction with a delta H. And all we do is we add them up, manipulate them, multiply through by 3, 6, divide, whatever, so that when we add up those reactions, we get what we want. Now, here's what we want. So the trick to doing this, I say, is let that final answer guide you, all right? And this is what we want. Use Hess's law to find delta H for that thermochemical equation. So this is what we want to find. So those other reactions, there's only 2 of them. Let the answer tell you what to do. So in other words, Lorena, if I look at this first reaction, this reaction A, this thermochemical equation A, do I want to do anything to it? You know, because I'm going to add up these reactions so I get this final one. Do I want to do anything to this first one? You're right. Why not? Right? Because the only thing in the answer is that little c, right? is big C. And C is on the right side. All right, it's on the reactant side. It's already there. And there's a 1 in front of it, and you want a 1 in front of it. So don't do anything. Because if you do anything, you're going to mess it up. That's the game plan. So you just write it down exactly as it says. A plus C goes to B. And the delta H was 200 kilojoules. Then you look at the second thermochemical equation, Paul. Do we want to do anything to it? Or leave it as is? Got to switch it around, right? The only thing that's telling you that is what compound? D. So you just find something that's there. So we got to flip it around. So fine, we flip it. B goes to A plus D. We're not going to multiply through by 3 or anything like that. But if I flip it, what's my new delta H, anybody? Positive 300. All right? Now life is going to be more complicated than this, so we should make sure everything's canceling on us, right? We've got the A's are canceled out, the B's are canceled out. You end up with just C going to D. So it works. And our final delta H will be what, Ashley? 500 kilojoules. So that's the game you're playing for Hess's law. The second way to get the enthalpy for our thermochemical equation. Okay, not so bad. This is a lot easier than what we just took a quiz on, I think. All right? Okay, there's one more way, the third way, to get the enthalpy for a thermochemical equation. I think you're going to like this. Use tabulated values of, what is that? All right? Because I could sit here, Megan, and say delta H0 with a little f on it every time I see that, but I shouldn't. What is that symbol called? It's not an easy question. Whenever you see a superscript 0, you're supposed to say standard. On pretty much any symbol in chemistry. Whenever you see a superscript 0 on a variable, you call it standard. Enthalpy, that's the H part. Standard enthalpy, and the little f is of formation. Standard enthalpy of formation. So what they did, what they call them thermodynamic chemists, work with these sorts of things. For every compound known to man, it has a tabulated standard enthalpy of formation. Carbon dioxide gas, carbon dioxide solid, oxygen gas, water, ibuprofen, whatever, they all have standard enthalpies of formation. They're just tabulated. We just Google it, right? And you can get the enthalpy for a reaction. Now notice how it's not just any enthalpy, though. It has a little superscript 0, so you should say standard. You can get the standard enthalpy for a reaction. Okay, now that's going to be at some particular pressure and some particular temperature, so you're kind of restricted in that sense. But you can get an idea. So the standard enthalpy for a reaction is the enthalpy of formation of all the products. Look them all up. Look up the standard enthalpy of formation of all the products in those tables. And then you look up all the standard enthalpy of formation of all the reactants. Add them all up and just subtract the two. So it's not so bad. And why does this work? It pretty much works because of what we talked about at the beginning. As long as you start at the right spot and end up at the right spot, it doesn't matter how you got there. You get the same answer. So we're just going to go with a standard enthalpy route. But you get more detail with that kind of stuff in more advanced classes. But that's the gist of it. So we're not going to Google all this stuff. I gave you a little table of the standard enthalpies of formation. See if you can figure out how to get the standard enthalpy for that reaction. Okay? Now I gave you what you need to figure this out. So you want to find what the standard enthalpy is for this reaction using that table. So pretty much follow what's in the box there. right? Add up the standard enthalpies for all the products, subtract out the standard enthalpies for all the reactants, and you should have it. Oh, but something's missing though. Manuel, did you ever already notice this? What's not in the table? Oxygen. Okay. I don't remember the homework right now good enough, but they might do this to you. They probably did. That's why I have it here. All elements. I think the word is allotrope, but how the elements exist in nature at 1 atmosphere and 25 degrees Celsius pretty much, but what's their most stable state? Right? Like in this room, how does oxygen, the element oxygen, exist? It exists as O2 gas, right? So, because this is energy, these are kilojoules. Well, if you're going to measure kilojoules, it's just like measuring anything else. You got to start from somewhere. Measure my height. You got to start from somewhere. Okay, you're going to start from sea level. You're going to start from the floor. You're going to start from the bottom of my feet. You got to pick a spot, and you got to be consistent. So the same way when they make these tables, they need a baseline. They need a zero energy. Where's their zero energy going to be? That's what they said. The rule is whatever that element is in its most stable state, that form, that's zero. So oxygen, that's zero. It's zero. They just want you to realize that. What if iron would have, well, it has to be. Notice how these subscripts are getting important. Because O2 with a little L on it is not zero, because that's not oxygen in its most stable state. So you'd have to Google that one. But iron should exist as a solid at room temp, 1 atmosphere. Its standard enthalpy of formation should be, Emily, 0. All elements are like that. So they may not, the homework may not be giving you those. It may expect you to realize that. So just, that's a trick in this, I guess. Okay. Okay, let's pick on somebody here. Sydney, how'd you do this? Yeah, where does that go, though? In the first bracket or the second set of brackets? Yeah, the second one. Okay, so that's negative 98.3. Now, do I multiply it by 2? Because there's 2 of them, right? So the game plan was to add up the standard enthalpy information for all the products minus the standard enthalpy information for all the reactants. Well, we're just lazy. We never do this anymore. This is really PBS solid plus PBS solid plus this guy written 3 times. So you have to write negative 98.3 in here twice. So instead of multiplying, I just multiply it by 2. So you do that for all the products. And then we've got 2 of these SO2 gases. So that would be a negative 296.8 plus a negative 296.8. You got to multiply that one by 2. So there's all my, hold it, products minus reactants. I wrote these on the wrong side. You guys didn't stop me, right? Products minus reactants. Products is this side. Okay, so what do we say? 2 PBOs. That's a negative 219 times 2. And we had SO2s, 2 times a negative 296.8. And then the reactants. So 2 of those lead to sulfur compounds, 2 times a negative 98.3. And technically, I guess you'd write 3 times 0, right, to make it look good. this is kind of, I like writing 3 times 0 because when you look at this a week from now studying for the exam, you remember what the heck you did. Products minus reactants. Did I screw up again? Products minus reactants. I didn't screw up, did I? Okay, what's the final answer? Lauren, did you get a number for this? Anybody get an answer for this? Lorraine, did you get an answer? What'd you get? 1,273. Anybody else get that? Connor, you get that?
No.
Oh, you guys both got what?
Negative 616.
Negative 616. Kenneth.
Since the negative 98.3 is being subtracted to make it positive.
Yeah, that's going to make it positive. Yeah. We better make sure we're doing this right. Okay, 219 is negative times 2 plus 2 times 296.8. That's negative. What's that? Plus. I got negative 835. Okay, now you get a point knocked off if you don't put units on here. What units do you have to put on there? Kilojoules, yeah, whatever's in the table. Okay. So, yeah, you could pretty much just erase the minus sign on the 98.3 and make it a plus. All right? I think your book didn't get updated. I sent in the wrong files. I changed this too dang often. Really? That sucks. All right. Well, let's go to the boards and hopefully we can. This should be a good day, right? So let's see if we can knock out a few of these and. Hopefully this didn't change on you. Find the enthalpy for this reaction. Carbon, hydrogen, and oxygen reacting to form, what is that, formic acid or something? Guys are being lazy today. Manuel, get up. It's good for you. Wake up. You guys are treating today like it's a Monday.
I'm still, well, because it is the first time I've had you this week. I'm still confused a little bit on how you are doing this exactly.
Which way? This way or the other one? This table?
I guess because, yeah, maybe because it was different. I don't.
So products minus reactants. So here's products.
Like I'm trying to figure out.
So add up these guys. They go in here. And then minus, has to have a minus sign, minus all the reactants.
Oh, so it's flip.
Yeah, so it's always products minus reactants.
Okay, so
Yeah, products minus reactants. So in this first example, remember, let the answer guide you. Let the answer guide you what you got to do. Odds are you probably will. It'd be more realistic if I gave you a whole bunch and you had to pick them. All right? But odds are you're going to have to end up using all three. So it looks like that third one, the one with water, you're just going to have to look at the other two reactions that you wrote and see what to do with it. Because notice in the very first reaction it has water in it, H2O. So you got to get rid of it because it's not in the final answer. Start being lazy today.
I
Megan.
want to make sure I have it in here.
Yeah.
And I never write it when I'm at the board.
Well, you don't need it. The whole idea is for you to learn how to do it.
I'm doing it.
And then it's being recorded online. So in this very first, just to make sure everyone's on the right track here, what'd you do to the very first reaction? Did you do anything to it? Flip it. Flip it around, because exactly. That big molecule is on the product side. And there's only a 1 in front. So don't multiply through by anything. Just flip it. And Stephen, what'd you do to the second reaction? You haven't got that far?
We just move the O. We just move the O to the other side on the second one.
Well,
Or we just leave it.
look for. My game plan in this is, see how oxygen is in more than one reaction? So don't even mess with it. Don't let it guide you. Find something that only shows up in our answer. So for that second reaction, what compound can you say, hey, that only shows up in the final answer? That carbon, that C graphite. That's what you go by. That's how I do it. So it's on the right side. I just got to do what? Add 2 or multiply by 2? Multiply everything by 2. Do I multiply the delta H by 2 also? Yeah. Multiply through by 2 in that whole thing. But don't flip it. So if you add up things now, you're not going to get that final answer. And you got to use that third reaction. Well, Dylan, you figure out what to do with that third reaction?
Multiply by 2 again, right?
Multiply by 2. Do I need to flip it or anything?
No, because I used a hydrogen gas.
Yeah.
On the reactant side.
Yeah, exactly. Yeah, if you flip it, you're going to mess it up. Right? Okay, you want those waters to cancel. So Dylan said multiply that third reaction through by 2 and it should work out.
And you just cancel, right?
And then cancel everything and make sure it works. Good. So things should cancel out and you should get the final answer. If you don't, then something's messed up. It work, Emily? Okay. What did you get? What did you get as a final delta H? Negative 486 kilojoules. Anybody else get negative 486? Okay, good. So let's make sure those are gone. Let's see. These guys are gone. Those guys are gone. That's about it, right? So all that I have left is 2C graphite and 2 hydrogen gases and an oxygen gas. That gives my compound. Well, that's what they wanted. So it works. Right? So if you got it, try the next one. If not, let me or somebody help you out here.
So our answer on the test is both of these.
Yeah, you have to have one with that. Yeah.
Did you add them?
Yeah, whatever you end up over here, you got to add them up.
I'll just pause it because we did it in the beginning. Yeah, let me go.
But you also have to.
Mm-hmm.
Can you divide this one since there's not another
Let's see. You want to end up with this. So what's a compound in here that only shows up in here?
Well, yeah, I mean, it's on this side.
Yeah. NH3, right?
Yeah, but we only need one of them. And
Only
there's
need
no,
one
none
of
of
them.
them in all the other rest of them.
Yeah, so you only need, yeah, and NH3 doesn't show up anywhere else. So that means you're going to have to do what to this reaction? First, it's on the wrong side, so you're going to have
Yeah, I
to,
flipped it,
you have to
yeah.
flip it, but then there's only one of them, so
Do you divide?
divide through by 2, everything.
Okay.
So, or multiply by half if you like prefer multiplying, but same thing. Mm-hmm.
For the last one, you have HCN on the product side, but you also have H2 is on the opposite side. So now what do you do?
Okay, so what, notice how when the only thing I go by is, see how H2 is in the other reactions. He's way too complicated to watch because H2 is influenced by every single reaction it's influenced by. So you'd have to really have a good brain to see what to do with H2. So what I do is I pick a compound that only shows up in the answer, and that is HCN. So that's what you go by.
Right here. You divide by 2.
Right, so how I started out this next one is you got to find a compound that only shows up in the answer, and that's NH3, ammonia. So that's what I go by. Ammonia's on the wrong side, and it has the wrong coefficient. So you got to flip it and divide through by 2. Play that same game for everything. See if you can get it to work out. Where did I screw up? Oh, I'm just going by methane, CH4. Don't go by, don't go by hydrogen, because hydrogen shows up in other places. To me, that's a real trick to doing this, is you go by methane, not hydrogen. Don't go by hydrogen, right? Don't go by hydrogen, because hydrogen shows up in every single reaction. Look at that. Hydrogen's here, hydrogen's here, hydrogen's here. Do not go by hydrogen. Go by methane. Otherwise, you're bound to screw it up. HCN. So now I'm going to go by the HCN, hydrogen cyanide. Just divide through by 2. And 1 1/2 and 3/2, that's just 1.5, 1.5, that's 3. Tanya, what'd you get for delta H? Around 256? So did you get around 256 kilojoules as the final answer? Okay. Good deal. All right, one more. And we can call it a day. Ashley, what'd you get as the final answer?
Oh, I got them.
Oh, you haven't. Oh, what about the next one? You haven't got the next one? Steph, did you get an answer? Negative 39? Kenneth got negative 39. You guys get negative 39? Oh, okay, good deal. Alrighty. Got screwed today. You got no bang for your buck today. You got burned 5 minutes. We're done already. So you get negative 39. Have a good day. Otherwise, let me help you out.